Let's look at binary hypothesis testing from a different perspective, the likelihood ratio and the receiver operating characteristic, or the ROC. Okay, now this second term, the receiver operating characteristic, I'll just say this once. It comes from radar. It was historically developed for radar purposes, so it sounds like a bit of a strange name. We'll usually just abbreviate it. We'll see that later. Okay, so remember from the last video, we introduced this framework of binary hypothesis testing. Okay, what does that mean? Well, it means that there are two hypotheses, H0 and H1, and they partition the underlying sample space. And you get an observation Y whose values are going to be drawn according to some conditional distribution. In the discrete case, what you're going to have is a conditional PMF. It'll either be P of Y given H0 if H0 occurs, or P of Y given H1 if H1 occurs. In the continuous case, you'll have a conditional PDF. You'll have F of Y given H0 if H0 occurs, and you'll have F of Y given H1 if H1 occurs. And you need to come up with a decision rule that takes in Y and outputs 0 if you think the hypothesis is 0, and 1 if you think the hypothesis is 1, based only on looking at Y. So that's what we looked at in the previous video. And we're going to revisit the decision rules, the ML and MAP rules that we developed from the perspective of this object called the likelihood ratio, okay, L of Y. And L of Y is just a function that takes the conditional PMF of H1, divides it by the conditional PMF of H0 in the discrete case, or in the continuous case, I take the ratio of F of Y given H1 over F of Y given H0, and that's for continuous. And this is just a convention to put H1 over H0, and we're just going to leave it like that. But we're going to see that changing to this perspective actually lets us go quite a bit farther in doing examples and solving problems in some cases. Okay, so to summarize, the maximum likelihood rule, or the ML rule, we remember that that was just going to try to figure out which hypothesis best explains the observation. In terms of the likelihood ratio, we're going to decide 1 when the likelihood ratio is 1 or larger than 1, and 0 when it's less than 1. We could also take the log of the likelihood ratio, and that would convert this check into checking whether it's greater than 0 or less than 0. And just to put it on the same slide, remember the likelihood ratio is the ratio of the conditional PMFs in the discrete case and the ratio of the conditional PDFs in the continuous case. Okay, so you might see this terminology around that this ln, so natural log of ly, the likelihood ratio, is the log likelihood ratio. And this can sometimes help us simplify the form of the decision rule. Okay, so when we have a particular decision rule, sometimes taking logs helps us get rid of some terms. We'll see an example. For the map rule, it's the same idea, except we're just going to have a different threshold. Okay, so we have this function d map, and it's going to be 1 when the likelihood ratio is greater than this ratio of the hypothesis probabilities, pH0 over pH1, and 0 when it's less than that. In terms of log likelihood ratio, it's the same thing. I just take log of the ratio of pH0 over pH1. Okay, and I just see which one is greater, and I decide 1 or 0. And why does that make sense for the map rule? Well, remember the map rule, the way we were deciding is we were weighting the conditional PMFs by the probabilities of the respective hypotheses. So I can just shift some terms over to see what that looks like. So I can form the likelihood ratio on one side, and I'll see that the probability of H1 shifts over to the other side, and I get exactly the threshold that I'm comparing to. Okay, so here's the likelihood ratio, and that's exactly why I have this rule. All right, well, let's see an example. Okay, in this example, we're going to have hypothesis H0, and under hypothesis H0, I'm going to observe a Y, which is going to be binomial, and it's going to have parameters n and p0. Okay, so the probability of success is p0. Under H1, Y is going to be binomial n with parameter p1. In the previous video, we actually worked out an example that was pretty much just like this, except we gave specific values for n and p0, and we're going to actually plug those in at the end and see how that works out. But for now, let's keep it abstract. So we're going to just see that the ML rule is going to decide, the likelihood ratio. Let's do the likelihood ratio first. So here's the likelihood ratio, py given h1 over py given h0. It's n choose y times p1 to the y times 1 minus p1 to the n minus y over n choose y times p0 to the y times 1 minus p0 to the n minus y. So I just worked out the form of the binomial PMF in both cases. And I took the ratio. So one nice thing about the likelihood ratio is often terms will cancel out. Here I'll see that n choose y is going to cancel out. So I'm going to do that. And I'm also going to combine all the terms that are raised to the exponent y. So I'm going to get p1 times 1 minus p0 over p0, 1 minus p1, all of that raised to the y. So if you compare that to the thing on the left, you see all those terms are sitting there. And I also have this thing which doesn't depend on y, which is 1 minus p1 raised to the n1, raised to the n, and 1 minus p0 raised to the n. Okay, so then the ML rule is just going to take this likelihood ratio and say that I decide 1 when this likelihood ratio is greater than or equal to 1 and 0 otherwise. So it's going to be 1 whenever this function, which we just wrote out, it's p1, 1 minus p0, p0, 1 minus p1 raised to the y times 1 minus p1 to the n over 1 minus p0 to the n. So this whole thing, if that's greater than or equal to 1, I decide 1. And if it's less than 1, I'm going to decide 0. Okay, so this is the form of the ML rule that I get from the likelihood ratio. And it's general, but maybe I could simplify it more. Okay, so I'm going to use the log likelihood ratio. And what I'm going to try to do is get this term y on its own. So I just want to see something that involves y a little bit more directly. So let's see, what does the log likelihood ratio look like? Well, log of the likelihood is log of this whole expression. So it's some factor p1, 1 minus p0 over p0, 1 minus p1, all of that raised to the y, times another factor, which is 1 minus p1 to the n, 1 minus p0 to the n. All right, so when I take the log of that, I can take the y out. So, and then I get log of p1, 1 minus p0 over p0, 1 minus p1, plus another term, which is n log of 1 minus p1 over 1 minus p0. So I allow the exponents to come down. And now I see that what I'm doing in the ML rule, if I look at it from the perspective of the log likelihood ratio, so remember with the log likelihood ratio, I'm now comparing to 0. So if it's greater than or equal to 0, I decide 1. Less than to 0, I decide 0 because log of 1 is 0. And so now I'm comparing y times some constant, which I have to work out from the parameters. So log of these parameters, is that greater than or equal to minus n log another thing just involving the parameters? Okay, so this is a bit simpler. I see I just have a threshold rule based on the value of y. And if you think about it, so let's just take a moment and think about this. Let's just say that p0 is smaller than p1. What I kind of expect to see is that when y is larger than a certain value, meaning I have more successes, I'll decide h1. And when y is less than a certain value, I'll decide p0, I have less successes. And let's see if the numbers from the previous video's example bear that out. So if you remember, in the previous video, we worked out an example using a table. And in that table, we had binomial with n equals 3, p0 equals 1/2, and p1 equals 3/4. And if you plug those numbers into this formula, you'll get y times the log of 3/4 times 1 minus 1/2, 1/2 times 1 minus 3/4. Is that greater than or equal to minus 3 log 1 minus 3/4 over 1 minus 1/2? And so that simplifies down to y log 3 greater than or equal to minus 3 log 1/2. And that simplifies down to y greater than or equal to 1.89. And since it's discrete, what that means is y is either 2 or 3. Okay, because y in this case takes integer values and the highest possible value is n. So the only values of y that satisfy the condition that it's greater than or equal to 1.89 are 2 and 3. And this is exactly the ML decision rule we worked out with the table before. So it's the same thing. Okay, let's do a continuous example. This is actually a really important example in many contexts. It's basically just trying to separate two means seen through Gaussian noise. So when h0 occurs, y is going to be Gaussian. Let's say that it has mean minus a, variance sigma squared. And when h1 occurs, we're going to also assume that y is Gaussian, but we're going to assume that the mean is going to be plus a. Okay, so it's symmetric about 0. It's either minus a or plus a. It has the same variance sigma squared. I'm going to assume that a is positive. You could have generic means, mu1 and mu0, but that would just kind of overcomplicate the notation. This kind of captures most of the intuition. So here's the conditional PDF in red under h1. So we see a Gaussian with mean plus a. And here's the conditional PDF under h0, and we see a Gaussian PDF with mean minus a. Okay? And what we want to try to determine here is what is the ML rule? Okay? So one way to do that is to use the likelihood ratio or the log likelihood ratio, but we can just look at this plot and guess that the ML rule is going to decide for hypothesis 1 when the value of y is greater than or equal to 0, because that's exactly where the red curve goes above the blue curve, and it stays above it. And it says h0 when y is less than 0, because that's when the blue curve is higher. Okay, so we're just going to check that that holds up with the log likelihood ratio. Okay, so the log likelihood ratio is just the logarithm of the ratio of the PDF. So I have 1 over root 2 pi sigma squared e to the minus y minus a squared over 2 sigma squared. So that's the conditional PDF of y given h1 because it's Gaussian with mean plus a. And I have the same form of the PDF under h0, except that the mean is going to be minus a, so it ends up as a plus a here because I'm subtracting minus a. Okay, so the constants get crossed out, and I have log of e to the minus 1 over 2 sigma squared. Opening up the squared, I have y squared minus 2ay plus a squared plus 1 over 2 sigma squared. And then I have y squared plus 2ay plus a squared. So I can cross out the y squareds, cross out the a squareds, and so I'm left with 2ay over sigma squared. That's the log likelihood ratio. So the ML rule will be 1 when this is greater than or equal to 0, because I've taken the log, and 0 when it's less than 0. Okay, well, when will that happen? Well, I just plug in what I found for the log likelihood ratio. I get 1. That's when 2ay sigma squared is greater than or equal to 0, and I get 0 when 2ay over sigma squared is less than 0. And okay, none of those constants really matter. They're all positive. All I need is that y is greater than or equal to 0, and 0 when y is less than 0. Okay, so this checks out. This is the same thing that we got from just staring at the plot. And that's great. So we see that the math checks out with what our intuition should be with what the picture gives us. All right. So from here, what we want to be able to do is work out the probability of error. Okay? So that's what we're going to try to do. So here's the same plot. So we're just going to keep all of this stuff up here. I've moved the ML rule up so that we can just see it on the right. And we're just going to ask ourselves, what is the probability of error under the ML rule? Okay, and I'm just going to remind you of the definition of the probability of error. It's basically when I make a mistake, I pick the wrong hypothesis. So either I say it's h1 when it's actually h0, that's a false alarm, or I say it's h0 when it's actually h1, that's a misdetection. And those are weighted by the probabilities of the hypotheses. So the probability of false alarm happens when y falls into the decision region for hypothesis 1, that's A1, but H0 actually occurs. So that's this green region, A1, where I'm deciding 1, and that happens when y is greater than or equal to 0 in this case. So what's the probability that y is greater than or equal to 0 under H0? Well, I just integrate its conditional PDF from 0 to infinity, and that turns out to just be the Q function evaluated at 0 minus the mean, which is minus a, over sigma, which is Q of a over sigma. Okay, and the probability of misdetection is when y falls into the region where I decide 0, that's A0, but H1 was actually the thing that occurred. So that's when, in this particular case, when y is less than 0 under h1. And to get that, I integrate from minus infinity up to 0, the conditional PDF of y given h1. And then to get that, I can just use the phi function because it's Gaussian. I have 0 minus the mean, which is a, over the standard deviation, which is sigma. And so again, this turns out to be q of a over sigma by the properties of the phi function. And so I can combine these two things together. So I have the probability of error is q of a over sigma, probability of h0, plus q of a over sigma, probability of h1. And since probability of h0 and probability of h1 have to add up to 1, I just get q of a over sigma. Okay, so in this special case, because of all the symmetry that we had, I could just immediately go for the probability of error without actually specifying the probabilities of h0 and h1 explicitly. Okay, so it just worked out that because I had equal false alarm and misdetection, it was the same. So what is the map rule if I actually have the probabilities? Okay, so the map rule is going to actually use the probabilities of h0 and h1, and we're going to work that out and figure out its probability of error. Okay, so the map rule, if you remember, is just going to come and say 1 when the log likelihood ratio is greater than or equal to the log of the probability of h0 over probability of h1. Okay, so I'm going to weight the hypotheses by their probabilities, and that's going to end up in this ratio in this logarithm. And when it goes the opposite way, I'm going to decide 0. Okay, so all I need to do here is just plug in the log likelihood ratio, which I know is 2ay over sigma squared, and then I just move it over the other side. I have sigma squared over 2a, log of the ratio of these probabilities, probability of h0 over probability of h1. That's when I'm going to decide 1, when that's, y is greater than that constant. And otherwise, I'm going to decide 0. All right, well, that's kind of a lot to drag around. So what we're going to do is just call this thing temporarily. We're going to call it beta, which is sigma squared over 2a, log of probability of h0 over probability of h1. Okay, and I'm just going to use this beta notation just on this slide just to make it a little easier for us to see. Let's say in this particular case, beta ends up being positive. So I'm going to decide 1 on the right side of beta and decide 0 on the left side of beta. Okay, and so the regions I'm going to get for the false alarm and misdetection are just by integrating on the other side of that line, and adding them up by weighting by the probability of the hypothesis gives me the probability of error. So probability of false alarm is when y falls into the decision region for 1, A1, under H0. So the decision region for 1 is this part to the right of beta. So the area of y, when y is greater than or equal to beta under H0, is integrating from beta to infinity the conditional PDF of y given H0, and that's going to be the q function of beta minus the mean, which is minus a, over sigma, and we can see that now highlighted in green under the plot, so it's the area under the blue curve, which is in green. So that ends up being qa plus beta over sigma. Okay, and for misdetection, that's when y falls into the decision region for 0. That's this orange region, right? So the orange region is less than beta, and that's when y is less than beta under h1. So I integrate from minus infinity up to beta, conditional PDF of y given h1, y, and then I get this big orange region under the curve. And so that ends up being the phi function beta minus a over sigma. And if I switch that to the q function, it's q of a minus beta over sigma. Okay, so that's what it is. It's not quite as simple a formula, but still it's something I can just plug in and work out for the map rule. And I remember that the map rule is always optimal if I have the probabilities of the hypotheses, and the thing that I care about is probability of error. Okay, so that kind of brings us to this question. So I have the probability of error. That's what we've been working with. It's the probability of false alarm times probability of h0 plus probability of misdetection times probability of h1. That's a very useful performance metric. There are places where that's the thing that makes sense. But okay, here's one problem. In order to compute it and optimize against it, I need to know the probabilities of the hypotheses. But in some cases, it's not going to make sense for us to model these explicitly. I may not have enough data. It may not be a sensible question, right? So let's say I'm trying to watch out for some unidentified aircraft coming into range of a radar. Okay, so that's my game. I don't want this aircraft to show up. How am I going to assign that a probability? This is just something I don't really know about. I've designed equipment to detect it, but I don't really have a grasp on those probabilities. What I can do instead is I can start to worry about the trade-off between false alarm, so thinking that it's there when it's not, and actually detecting it when it's there. Okay, so I want to see what the tension is between these two quantities. Okay, so I want to detect things when they're there, but I don't want to have false alarms. Well, okay, let's flip things around a little bit. So the probability of detection, let's call it P sub D, that's going to be the probability of deciding one, given that hypothesis one occurred. Okay, so very simple. All it's going to be is a probability that I land in the decision for one, and one did occur. So it's 1 minus the probability I landed in the decision for 0, which is 1 minus the probability of misdetection. And that makes sense. The probability of detection is just the complement of the probability of misdetection. Okay, so great. So the receiver operating characteristic, abbreviated as ROC curve, that's going to be the optimal trade-off between the probability of detection, okay, so this thing that we just defined, P of D, not misdetection, but detection, and the probability of false alarm, which is P of FA. Okay, so we're going to put P of D on the y-axis and P of FA on the x-axis, and this is just how this thing is traditionally defined, and in fact the name is even from this radar context. So this is just a traditional name, it's the ROC curve, and you'll see that in other contexts, but people just still use that name. Okay, so how can I find this optimal trade-off? Okay, it turns out it's not so hard. Maybe it's a little bit to absorb, but it's not such a hard thing to do. So what you need to do, first thing, is you need to figure out the likelihood ratio. Okay, so I'm going to find the likelihood ratio for my problem. Let's call it L of y. And then I'm going to create what's called a likelihood ratio test with threshold t. Okay, so I'm going to define this as t, d sub t. And what I'm going to do is just decide 1 when the likelihood ratio is above or equal to t, and 0 when it's below t. Okay, and then what I'm going to do is now I'm going to vary t. So I'm going to start at t equals 0, and I'm going to go all the way up to t equals infinity. And I'm going to calculate the decision region for 1 when basically, so this area where I'm deciding 1 using this likelihood ratio test with value t, with threshold t. So I'm going to have that decision region. And then for a particular t, then I'm going to come and calculate the probability of false alarm. So the probability that I fall into that region A1 for t, and the probability of detection, not misdetection, but detection, again for A1. I'm going to calculate both of those. And sometimes it's easier to work with the likelihood ratio directly. So this thing that I just wrote in these definitions is what we're used to dealing with from before, which is the probability that y falls into the decision region. But you can write that directly in terms of the likelihood ratio. Sometimes that's easier. So in this case, it would be probability of Ly being greater than or equal to t under H0, or Ly greater than or equal to t under H1. And all I do is I then, as I vary t, plot the resulting pairs of false alarm and detection probabilities. Okay, so I get a curve. So there is my curve. All right, so I have this green curve that just showed up in this plot. What are the properties of this curve? Well, one is it's concave. Okay, so concave means that if I pick 2 points on this curve and I draw a line between them, the curve will always lie above that line. Okay, and in fact, it always lies above the line. The specific line we're talking about is the line where probability of detection is equal to probability of false alarm. Okay, so that's that line here. And this makes sense because basically you can achieve this line without any information whatsoever. You don't need to look at y to make this happen, right? So for instance, let's look at the 0, 0 point. I can always achieve that point by always deciding 0. I never detect anything, so the probability of detecting something then is 0, and I never make any false alarms because I'm never declaring 1. On the other side, I could always decide 1, 1 by always saying 1 occurs, so I always detect when something occurs, but I also always make a false alarm, and I can kind of do that randomly and achieve any point in between. So that's not an interesting line because I can do it without ever looking at my observation. So I want to be above that line. Okay, so what the ROC curve is doing for us is it's telling us the optimal or rather the highest probability of detection that can be achieved for a given false alarm budget. Okay, so I have a given probability of false alarm budget that I'm willing to spend, and this tells us what's the best probability of detection I can attain, which makes sense. So if I'm trying to detect my aircraft with this radar, maybe I'm only willing to tolerate a certain number of false alarms per day, so I just set that level, and then I try to get the best possible detection that I can. Well, let's see how this works out through two examples. We're going to do a discrete example and then a continuous example. Okay, in my discrete example, I'm just going to do it with a simple table. So let's write out a table of probabilities. Okay, so here's my table. Y can take the following values, 0, 1, 2, and 3. And I have the conditional PMF of Y given H0, and I have the conditional PMF of Y given H1. I'm just going to write out their values. We're just going to take them face value. I'm going to also write out the likelihood ratio once I have my values. Okay, so we're going to work directly with that. Okay, so let's go entry by entry. So I'm going to have a half, a fourth, an eighth, and an eighth. You can check that adds up to 1, or an eighth, a fourth, and a half. So very simple conditional PMFs. So their likelihood ratios are a fourth, a half, 2, and 4. You can just check that out. Okay, so this is what we're working with. Well, what is my likelihood ratio test going to be? Well, as always, it's pretty simple. All I'm going to do is just take the likelihood ratio and compare it to this threshold t. If it's greater than or equal to t, I say 1. If it's less than t, I say 0. Okay, so my decision region is just when the y's that fall into this part where I say that I decide 1. And so the probability of false alarm is just the y's where I'm deciding 1 under H0. And my probability of detection, not misdetection, but detection, is just going to be the probability of y falling into A1, given that H1 occurs. Okay. So from from 0 up to 1/4, I'm going to have a threshold that falls before anything else. So basically, if you look at the likelihood ratios, if t is up to 1/4, then basically everything going forward to the right here, so basically I'm going to be deciding for decision 1, so the likelihood ratio is going to be greater than this value of t for everything. A fourth is greater than a fourth, a half is greater than a fourth, 2 is greater than a fourth, 4 is greater than a fourth. So I'm always going to decide for 1. And so all of the values 0, 1, 2, and 3 are all going to fall into the decision for 1. Okay, so now I can figure out my probability of false alarm. I'm just going to add up all of the values that correspond to that. That's going to be 1. And probability of detection is also going to be 1 because I add up all the values that correspond to it and I get 1. So I have this point here. Okay, so here's my ROC curve. It starts out with this purple point on the right. Now I'm going to look at the threshold values that fall between a fourth and a half. And I'm going to see that that's basically everything except this likelihood ratio of a fourth. So now my threshold is strictly larger than a fourth. So I'm only capturing the 3 values on the right. So this decision region is going to have 1, 2, and 3 in it. Okay, because those are the likelihood ratio values that are larger than a fourth. My probability of false alarm just ends up adding up those values, a fourth, an eighth, and an eighth. So I get a half. And my probability of detection is going to also add up the corresponding values. I'm going to get an eighth, a fourth, and a half. That's going to be 7/8. I'm going to draw that point on my plot. Let's go now that we're strictly greater than a half and less than or equal to 2. So now I'm only going to have the 2 values here, so shown in green. So A1 is only going to be y equals 2 and 3. Those are the only likelihood ratios that are greater than a half. And so probability of false alarm, I add up the 2 values. That's an eighth and an eighth. I get a fourth. Probability of detection, I add up the 2 values. That's a fourth and a half. I get 3/4. Okay, I'm going to draw that point in green. Strictly greater than 2, I'm only going to have 1 value now. So 4 is the only value that's going to be strictly greater than 2. So the decision region is just going to be y equals 3. Okay, and so my probability of false alarm is just going to be the corresponding probability. It's an eighth. okay? And the probability of detection is going to be the corresponding probability. It's just going to be 1/2. And I'm going to plot that point on my chart here. Okay, and then actually I have one more thing left to do. I can put the threshold above 4, so I don't pick any values. So my decision region is now empty. I never pick 1. So probably a false alarm is 0 because I never pick 1. And probability detection also is 0 because I never pick 1. That's this point on the bottom. All right, and finally to get my curve, all I'm going to do is connect these points. It's a discrete example. I'm not going to have a continuum of points. I'm just going to have this line connecting them. So we'll see that in gray, and this is going to be my ROC curve. Okay, so this is the best, for this particular example, for these two conditional PMFs, this is the best possible detection performance I could have for any given probability of false alarm as my budget. Okay, well, let's go back to our Gaussian example that we saw, and let's try to figure out the ROC curve as well. And you can do this in a slightly quicker way than I'm going to do right here, but I want to do it exactly according to the procedure that I gave you. Okay, so we already have the log likelihood ratio, so we're going to use that here. So I'm going to have log likelihood ratio. Remember, that's log of the PDF of y given h1 over conditional PDF of y given h0. That, in this case, is 2ay over sigma squared. If you forgot how we got that, you can just back up and you can see that that's what we derived earlier. And so since we have the log likelihood ratio, we know the likelihood ratio. The likelihood ratio just has to be e to the 2ay over sigma squared, okay? Because I already have the log likelihood ratio. Great. So then I can write down the likelihood ratio test because I have the likelihood ratio. All I'm going to do is I'm going to have this test, which is going to be 1 when e to the 2ay over sigma squared is greater than or equal to t, and 0 when e to the 2ay over sigma squared is less than t. Okay, and so now I can explicitly work out my probability of false alarm, right, for any given threshold. So the probability of false alarm for a threshold t is going to be the probability that the likelihood ratio, in this case, that's going to be e to the 2ay over sigma squared. When is that greater than t or equal under h0? So that's moving some terms aside and taking logs. That's going to be the probability of y being strictly greater than or equal to sigma squared over 2a log of t under h0. And remember that if z is Gaussian with mean, mu, and variance sigma squared, then the probability that this random variable z is greater than some value alpha is given by this q function, alpha minus its mean over the standard deviation. So in this case, so that's just a little reminder. So in this case, what that's going to mean for us is we're going to have q of the value we care about, sigma squared over 2a log threshold minus a, that's the mean, over sigma. Okay, that's the probability of false alarm for a given threshold t. And I can just do the same thing for the probability of detection, not misdetection, but detection. What we worked out before was probability of misdetection. Okay, so we're just kind of flipping it a little bit. So probability of detection is the probability, again, that my likelihood ratio is going to go be larger than or equal to t, okay, under h1 now, because I'm trying to detect something that actually occurred. And that's going to be the probability that y is greater than or equal to sigma squared over 2a log of t under h1. And so it's going to be, again, using this Gaussian property q of sigma squared over 2a log of t minus a, the mean, over the standard deviation sigma. And now what we're going to do on the next slide is we're going to plot these pairs, the probability of false alarm and the probability of detection for a given threshold t. And we're going to range the threshold all the way from 0 to infinity. And in this case, since it's continuous, that's going to give us a continuous nice plot. Okay, so what we're doing here is we're just plotting some of these values. So here, what I've done is in MATLAB, I plugged in a equals 1/2 and sigma equals 1, and I got a ROC curve, probability of detection versus probability of false alarm. Okay, and I did that by just varying t here. Okay, And actually, if you play around with it, it's simpler to not vary t, but to figure out one value that you care about, say probability of false alarm, take the inverse of the function that you have there, and then plug that in to get probability of detection. But we'll just leave that be. I'm not showing the code anyway. Here's another plot for a equals 1. So I'm increasing the mean, leaving the standard deviation alone. And you can see that the ROC curve has kind of shifted up and to the left, which is good, right? So the probability of detection for a given probability of false alarm has gotten better. And that is because the means are now more separated because 1 is larger than a half. And I'm going to try a equals 2 now. And now I'm going to see it's going to really shift up to this top left corner, which is great. So the best possible performance that I could have is what? Well, I want to detect everything. So I want to have probability of detection 1, but I don't want to make any false alarms. So I want to have probability of false alarm 0. For the Gaussian example, this can happen. So we can approach this performance, but what we can see from the equations above, this is going to happen for us as a over sigma is going to go to infinity. And the reason that happens is the conditional distributions will become increasingly separated, right? So they're just going to push apart from each other. So the area on which this overlap is going to occur is going to become smaller and smaller and smaller. And it has to really go to infinity before you reach that value exactly. And even though it looks really good here in this on this plot, which is a equals 2 and sigma equals 1, that's not quite accurate, because really, if we kind of zoom in there, we still have quite a significant probability of making some mistakes. It's just that, you know, as probability gets closer and closer to 1 or closer and closer to 0, maybe you need to take logarithms in order to see that better. And so maybe at some level, you need to have a different look at this plot or a different perspective to kind of appreciate that. Okay, that's it.